All right, we're ready to do another vector decomposition problem. I've got vector f pointing straight down, and I have an e1 and e hat 2. These are the directions I want to decompose this vector in. And it looks like a standard problem, except there's a little bit of difference between this problem and some of the other ones we've had. In particular, I'm not sort of writing the orientation of these basis vectors in terms of some angle theta like I did before. Instead, I have them sort of, or at least the e hat 2 direction, sort of along this sort of sloped line. And instead of characterizing that slope by some angle right there, I'm characterizing by these two lengths of a triangle, A and B. So I have to write my vector decomposition in terms of A and B, right? Not in terms of some theta, because I'm not given an angle theta. All right, so how does that sound? Even though it looks a little bit different, the principles are pretty much the same. So what I'm going to do is I'm going to take this vector f and use that as the hypotenuse of this vector triangle that I'm constructing. And the vector triangle has its other two sides parallel to the e hat 1 and e hat 2 direction. So I'm going to write this vector f. This is the vector f right there. I'm not sure why it's not labeled. I'm going to write that in terms of something that's along the, in this case, the e hat 1 direction, plus something along the, I guess, the minus e hat 2 direction right there. So there's my vector triangle. And that sounds good. Now I got to figure out the lengths of those sides of that vector triangle. And the way I did it before is I transposed an angle from this setup over here to this one over there. And I'm going to do the same thing. Although there's no theta or phi or whatever angle, there's no angle that's given, I'm just going to define one right here. So sort of internally, I'm just calling this one angle theta. And this angle theta is the angle between the vertical here and something in the e hat 2 direction. So the vertical here where f is aligned with, and something in the e hat 2 direction is that line right there. So this is angle theta right there in my thing. Now it looks like one of our previous vector decomposition problems, and I can write this vector decomposition in terms of that theta. So in particular, let me just so in the e hat 1 direction, that's this component there. That's that's opposite from theta. So that would have an f times sine theta. Notice that this component right here is in the positive e hat 1 direction, so I can put a little positive right there if I want to. And so that's the e hat 1 component. And then the e hat 2 component, it has a cosine there because this 2 component, there's a 2 component, that's on the adjacent side of the triangle. And notice that the e hat 2 component is in the opposite direction of the e hat 2 basis vector, so I put a minus sign right there. So there's my decomposition in terms of theta. But again, theta is not given to us. Instead, what's given to us are this a and the b. So what I'd like to do is write cosine theta and sine theta in terms of a and b, and it's really not that hard. If you recognize that this is theta right here, and the cosine of theta would be just the adjacent divided by the hypotenuse. So cosine theta, the adjacent is length a, the hypotenuse is a squared plus b squared square root, and therefore cosine theta is this expression right there. And of course you can check for yourself that sine theta would be this one, right? Sine theta deals with the opposite side, so length b in the numerator. And that's what I get. So I'm going to take these two expressions for cosine and sine, and I'm going to substitute them into my vector decomposition. So let's see what I get. There I go, I just wrote it. And again, all I'm doing is I'm substituting this cosine and sine into what I had below. And now I've got an expression for these components of my vector f. And I have it in terms of a and b. So there's my answer.